Kia ora, thank you very much for coming. My name's Jenni Stanley and I work at the University of Waikato, and today I'm going to tell you a little bit about sound underwater and the many things you can be observing, monitoring and listening for underwater, specifically in Fiordland. So I have a small soundbite for you here. This clip is from Moana Marine Reserve. Picture this, it's getting dark and the soundscape's starting to reach its maximum loudest level for the day. You'll hear some snapping shrimp. You'll hear grazing sea urchins. And marine mammals in the background. Underwater environments can emanate a cacophony of sounds, and different underwater habitats have unique sound signatures or soundscapes. Just as a bush environment is filled with sounds different to that of a city environment, different underwater habitats have distinct acoustic signatures due to its biological and physical makeup. I investigate the cause and effect of these variations, whether in reefs or estuarine environments, due to natural or anthropogenic processes, and relate these to greater ecosystem functioning. So underwater sound is a pervasive and dynamic property of all ecosystems, and habitats are comprised of a diverse range of abiotic or geophysical sounds, such as those that you see here: rain, storms, wind, earthquakes. Anthropogenic or human-made sounds, those from vessels, offshore construction or wind farms, and also biological. So underwater soundscapes hold a vast amount of biological information, reflecting the many vital processes in a realm where other signals are often very limited by light, visibility, and accessibility. However, as human activities along more of the Earth's coastlines and offshore regions are increasing, so too does the occurrence and intensity of anthropogenic sounds and its presence in the underwater soundscapes. There's been shown to be various potential effects of noise on marine species, ranging from changing one's behaviour to permanent hearing damage. However, we know little about the spatial and temporal effects, because many of these experiments are in controlled environments, and we know even less about the long-term individual and population level effects of noise. So why listen? This fundamental property of all habitats is still underutilised for the breadth of information it can hold. With the increase of human activities, climate change, and increased ecosystem degradation, baseline data sets are more important now than ever for understanding change in our marine ecosystems. Perhaps the more important question is, can marine systems cope with the ever-increasing levels of anthropogenic sound and environmental change? So currently I'm leading a program which combines passive acoustic listening technologies and analysis techniques to assess and effectively monitor New Zealand's protected underwater areas for improved marine protection. Fiordland actually chose me. Luckily, this is kind of opportunistic. We weren't planning to be in Fiordland, but with the great team kind of spearheaded by Doc, I've managed to spend nearly 3 years down there recording underwater. So I'm listening to all around the country. However, today we're here to talk about Fiordland. So this is a map of the high resolution array that we have currently in Moana, or the Five Fingers Marine Reserve, within Tamatea or Dusky Sound. So it's one of New Zealand's most isolated marine reserves, and there's growing concern that the increase in human activities in this area, especially cruise ships, and their effects on the habitats and the species that live within that fjord and marine reserve. So we currently have 3 sites within the marine reserve and 1 outside of the marine reserve just south of Anchor Island. Those little red dots indicate where we're listening, and it's an subsurface hydrophone mooring system, so you won't see anything on the surface. It's all underwater, creating as little artifact noise as possible. So what do we hear? You'll see a lot of these graphs from me today, and it's called a spectrogram, and I'll quickly run through just so you know what you're looking at for the future. Along the horizontal axes you have time, so it's on the scale of like 30 seconds odd, and on the vertical axes you have frequency range, so from low pitch to high pitch. And then the colour is the intensity, with red being loud and deep blue being really quiet. So along the way, we've identified a number of biological contributors in these acoustic recordings. A number of invertebrates like snapping shrimp, which sounds similar to bacon frying in the fry pan. Sea urchin grazing, where they have their skeletal teeth, their Aristotle's lantern, that actually graze on hard surfaces when they're feeding on macroalgae. They're a perfect natural amplifier that amplifies their sound within their test, and that emanates for really, really large distances. As well as many fishes, which many haven't actually been identified to date in Fiordland, so that's kind of the next steps. But we have plenty of really weird and wonderful sounds. As well as invertebrates and fish, we also hear a number of marine mammals, as Leah had 2 talks on both the bottlenose and the humpback whale. We also believe to have heard a couple of blue whales and possibly even a southern right, which we're still double checking on. As well as the biological, we're hearing a lot of abiotic noise, wind and waves, rain, funny that, lot of rain. And earthquakes, also an incredible number of earthquakes, which is really interesting as well. So what about the soundscape as a whole? We can pick out these little, sounds attributed to organisms, but what about the soundscape as a whole? And yes, this is a very full-on graph, but try to think of this as like a single number that gives us a metric of loudness over a period of time. So here you've got sound pressure level on the vertical and time along the horizontal. And this is just the variation in time of like one overall metric of loudness for this, these 2 areas. And as you can see, these 2 sites have a slightly different pattern in overall broadband level. However, it tells us at these sites that we have trends in the level and variance per season. So with winter showing some diel trends, so daily trends, peaks and troughs on a daily cycle. But in the winter, it's largely driven by episodic peaks, weather events. And in the summer, it shows, again, this very strong diel, daily 24-hour period patterning consisting of 2 or even sometimes 3 peaks, usually occurring at dawn and dusk. And this is all due to biological activity. And this can actually vary among sites as well. This is another way of looking at that kind of broadband metric of like how loud things are at a location over time. And this is just looking at over the 24-hour period, over the whole deployment during each season, and how that loudness changes throughout the day. And as you can see, the first one, Anchor Island, it's a sandy bottom habitat. The reef is a lot further away from the hydrophone. You don't have a huge amount of biological presence. However, FF2 and FF3 have these huge peaks, especially at dusk, but dawn and dusk at FF3, due to all the animals on the surrounding reefs creating these noises at dawn and dusk due to their activities. So how do we apply some of these observations that we have in these data sets? This is just a small snapshot. This data set is huge. We are finding dolphins and whales and fish and vessels, but how do we use this information from these data sets to tell us more about the health or status or change of these habitats? So we have some first order management questions that are asked by a lot of people. And one, if not only the most consistent theme raised by all stakeholders across fields, sites, locations in New Zealand and worldwide, is vessel presence. How many vessels visit our MPA? What are they doing? Huge interest in vessel behaviour within the MPA. It's often related to compliance, but also understanding tourism and visitation increase or pressure shifts away from specific areas of interest. So these are just 3 examples of different types of vessel behaviour, with the first one doing kind of a pass by the hydrophone, a larger boat, then the middle one, a smaller boat whizzing past, and you hear a very change in the frequency. So it's like brrr, and then it's like bzzz, and then just another activity where it's changing gear and things like that. So you can tell a lot about what the vessel's doing just by its acoustic signature. So a lot of sites are also interested in fine scale information on vessels. So this is just an example of a deployment between February and July inside at Taumoana and outside of the Marine Reserve. And this is looking at number of vessel detections via our machine learning algorithm at different 1 hour periods of the day over that entire period. So just the way of looking at it here is looking at, so what are the most, what time of the day is the most common to see a vessel within these periods of the year, and how many detections are we seeing? And you know, some of these total detection is up to 49 to 50 at certain hours of the day at Anchor Island between February and July, and then much smaller, as you can see, in the Marine Reserve. You can also break this down to day, season, however you want to have a look at it, really to understand visitation and whether it's the same vessel visiting or it's starting and stopping. So you can pretty much pass it however you're interested in understanding vessel activities. This program supports a number of collaborators with acoustic methods to answer some specific questions that visual monitoring can't always answer. Remember, acoustic sampling is occurring with these recorders 24/7, so they're listening all the time. So there's a lot of periods of time where we can't visualize, but we can be listening. And as you heard Leah's talk on bottlenose, we've done a lot around my sites as well on this species. And also Chloe. So Leah gave a nice summary here, just showing you the examples of what acoustics can kind of do. So what are the real next steps of this larger program? Well, this is just a tiny snippet of some of these first order analyses, being able to get some students on the case. So we're now working up some finer scale information on vessel presence and the overlap with some sensitive species such as humpback whales and common and bottlenose dolphins. Here we'll be comparing the presence with vessel presence and looking at creating risk maps. So when are these two activities the most likely to overlap, and at what levels are they going to be potentially masking acoustic behaviour of these animals, but also tell us a little bit more about these animals' behaviour around vessels as well. This work couldn't have happened without a huge team of support, Southern Winds especially, and all the team involved with working on the Southern Winds. Also a lot of people at the University of Waikato and hardworking students going through a lot of acoustic data. Yeah, thank you very much for coming.